Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing the concept of limiting and excess reactants in stoichiometry. So far we've been looking at chemical reactions in chemical processes like this one, when nitrogen gas reacts with hydrogen gas to form two lots of ammonia gas. And we've been looking at this idea of looking at how many moles that our reactants will combine and form how many moles of products. Saying, okay, so if we have 3 moles of nitrogen that react, that we're going to need 3 times that ratio amount of 9, so 9 moles to produce 6 moles of our reactant. Because we've been working with this idea of everything that we have is reacting together and is all being used up to make our products. But the reality is that in life, things don't work out that simply. Which is not to say that it's all wrong, but what we tend to be dealing with is a different reality. That is, the reality is that we often have one reactant which it decides how much product that we make, and another one that we have an excess amount of. So we call a limiting and excess reactant. All right, and so let me illustrate with a food analogy for you. Okay, I do love a good food analogy. So let's look at this idea of how we make a cheese sandwich. So to make a cheese sandwich, we have 2 pieces of bread plus 1 piece of cheese forming 1 sandwich. Apologies if this is making you hungry. Okay, but so look, I appreciate this is a bit of a simple analogy, but you'll see how this works in a moment. Okay, so 2 pieces of bread plus 1 piece of cheese forms 1 sandwich. Okay, so all the bread and the cheese that were there at the start are there at the end. Okay, but the idea is that they've changed form. They've rearranged in some way. They've gone from being separate to forming 1 combined product. So let's say, so what we've been working on with is this idea that we have 2 pieces of bread. So let's say each of these represents a piece of bread. Okay, clearly I'm not an art teacher. Okay, and then I've got 1 piece of cheese. 2 pieces of bread plus 1 piece of cheese. Therefore, how much do we make? We make 1 sandwich. Well, he's testing my skills. Okay? Don't judge me. So, I've got 2 pieces of bread, 1 piece of cheese, makes 1 sandwich. But that only really works if that's exactly the right number of everything that we have, that we only have 2 pieces of bread, we only have 1 piece of cheese, we only therefore make 1 sandwich. Or even let's say, okay, I start with 4 pieces of bread. Okay, I therefore need 2 pieces of cheese, and I end up making 2 sandwiches. Exactly. I don't have any leftovers, which is good. As far as, well, if sandwiches are concerned. Okay, and so I can use this process and use this ratio of things in my equation to say, all right, well, how much, if I have this, how much of this do I need? If I have these, how much of this do I make? If I want this, how much of this am I going to need? Okay, that's the whole concept of stoichiometry, being able to use moles and mole ratios to be able to look at reactants and products with this kind of mindset. But see, then what I get is that now, okay, well, let's say I have 4 pieces of bread and 4 pieces of cheese. What do? I want to make sandwiches. Well, I know that I need 2 pieces of bread for every 1 piece of cheese to make a sandwich. So these 2 and this one make a sandwich. These 2 and this one make a sandwich. But then I have this. I have 2 pieces of cheese left over. I have something which is in excess. That is, it's left over. Or it is unused. Okay, so I have 2 pieces of cheese that have not gone in to make a sandwich. I'd have to put them back into a fridge for another day for making me some other sandwiches, or I'd have to buy myself more bread. But if this is all I had, I can make 2 sandwiches, and then I have my 2 pieces of cheese left behind. Okay, so what I have is that I have one substance which has limited how many sandwiches that we've been able to make, and one substance which has been left over at the end. Okay, and so we call this one the limiting substance, or in this case, limiting reactant. Okay, if we wanted to translate this across to think about chemical reactions. Okay, so I have something that limits how much product we make. something which is left over at the end. Okay. Now, the great thing is, so this is a reality of most chemical processes we're talking about. The great thing is that we can use this concept to be able to predict. So we can then say, okay, well, we can then decide for a certain amount of stuff that we have, how much product are we going to make? And so I'm going to use this same quick analogy to show you that. So what I have here, I've now got 4 pieces of bread and I've got 1 piece of cheese. Okay, now that's probably a bit of a simplistic example to show you here, but it's fairly clear that there's only so many sandwiches that I can make with 4 pieces of bread but 1 piece of cheese. Okay, I know that either I'm going to have cheese left over or I'm going to have bread left over in the whole process anyway, but I can see that, okay, I need 2 pieces of bread and 1 piece of cheese to make 1 sandwich. Okay, so it's like then I've taken this and I've taken these 2. They've gone in to make the sandwich, so I have 2 left over. So in this situation, that this is now excess, my cheese was limiting, and then I could use this and predict how many sandwiches that I can make. I could look at it straight up and say, okay, I've got 1 piece of cheese, I need 1 piece of cheese for every 1 sandwich, so therefore I can only make 1 sandwich. This has limited how many sandwiches I can make, and it's also allowed me to predict how many of this I'm going to use up and how much is left. I could go, all right, I need 2 pieces of bread, so I take 2 out, the rest is excess. Okay, so now let's translate this into a chemical example. So what we have here is a chemical reaction between hydrogen and chlorine gases to form HCl, or hydrogen chloride. I'm using some little magnetic buttons here to help you to visualize exactly what it is that's going on here. Okay, so if we have a look at this, so I'm saying that 1 molecule of this and 1 molecule of this combine together to make 2 molecules of that. So that is, I take 1 hydrogen, 1 chlorine from here, and I take 1 hydrogen chlorine from here to produce 2 HCl. Okay, let me reset. But so let's say that I have 3 lots of H2 and 2 lots of Cl2. And now I've just got to decide, okay, which one's going to dictate how much product we make, which one's limiting, and which one is in excess. Okay, so I know that I need one H and 1 Cl for every molecule over here. Another one, and another one. And now I've run out. I have 1 molecule of H2 left over. So this one was in excess. I'm just going to do a little abbreviation here. And then this one was limiting. And so the amount of Cl2 that I had here was what dictated how much HCl that I had. Now, I can do that. Like this is really useful to kind of visualize, but I can actually make this prediction without having to move anything else like that. Okay, I can see for every 1 chlorine, I need 1 hydrogen. Okay, so that means I'm going to use this up faster, and I'm going to have some of this left over because of that. For every 1 molecule of chlorine that I have, I produce 2 molecules of HCl. So if I have 2 molecules of chlorine here, I'm going to make 4 HCl, and that's exactly what we did. We just went through the process of mechanically actually kind of sorting it through. But what I'm trying to get at is this idea that we can work this out theoretically without having to try and churn through the tedious process of matching these things up. We can, with practice, we can look at what we have and make the prediction. Okay, and so then we could take this sort of reaction, you know, and then say, all right, well, let's say that this is the situation we'd have. For every 1 H2, I need 1 Cl2. I've got more of this and less of this. This will be used up faster. And so then our excess and our limiting swap around in this situation. For every 1 of these, I make 2 of these. So I'm going to end up with 2 molecules of that. Now, we also know that these are representing molecules, but we can also do this in terms of moles. If I have 1 mole of this and 2 moles of this, okay, this is limiting. I've got 1 mole of this. I'm going to produce 2 moles of HCl for every mole over here. So I'm going to end up producing 2 moles over there. So the same sort of idea of ratio, scaling it up, looking at our limiting reactant to decide how much product we make. I'm going to look at one last quick example where it might not be quite so clear cut. So let's say this is the chemical reaction that we're working with. We've come back full circle to the one that we started by looking at. When 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 ammonia molecules. Okay, so that is for every one over here, we need 1 red and 3 blacks. Like that. 1 red, 3 blacks. Okay, that's showing you how they were rearranged like that. Or reset. But let's say this is the reaction mixture that we have. We've got equal numbers of nitrogen and hydrogen molecules, 3 and 3. So now we get to a bit of a tricky situation. We have to say, well, how are we going to work out how much product that we make? How are we going to work out which one runs out first? They have equal amounts. But the reality comes down to the ratio that we have in our reaction. For every 1 molecule of nitrogen I have, I need 3 times as many molecules of hydrogen. For every 1 mole of nitrogen I have, I need 3 moles of hydrogen gas. And so, if I ask myself the question of which one runs out first, I can see that I'm going to run out of hydrogen first before I run out of nitrogen. Okay, so let me show you that in action. Okay, remembering that we're working with the same ratio as before, then do the same thing, and I have run out of hydrogen gas, and I have 2 molecules, or 2 lots of nitrogen left over. Excess and limiting. Okay, so by asking myself which one runs out first, I've been able to then determine or predict how much product I make. I know that for every 3 molecules of this, that I make 2 molecules of that. So even before I actually started manipulating the magic buttons to show you, I can actually predict and say, all right, this is going to run out first. I'm going to then have 2/3 or 2 lots of this for every 3 lots of that. Okay. Now the beauty of this approach is that, look, I've been working with some kind of fairly simple kind of magnetic buttons here to try and illustrate the point for you. And I appreciate that it also means that I'm looking down a little bit too much when I'm working on this video. But the idea here is that we can then be able to look at this in terms of just pure numbers as well. So let me just get rid of this in a second, and I'm going to start dealing with something that's a little bit more complicated. Okay, so let's say that I have 5 moles of nitrogen gas, and I have 12 moles of hydrogen gas. Okay, now at the start, I'm going to have 0 product. Okay, so if I'm going to work with a B, C, A table, okay, so I've got 5 moles of this and 12 moles of that to start with. So what I then have to do is, in order to work out which runs out first, is I've got to run through 2 scenarios in my mind. Firstly, what happens if the nitrogen limits and all of this runs out? How much hydrogen do I need? And then I do the opposite. I say, all right, well, if hydrogen's the limiting one, how much nitrogen will I need? One of those will run out first and we will end up with a positive amount of the other thing. The other scenario won't work at all. We'll end up with a negative. Okay, let me show you how that works. So let's say, first of all, that all of the nitrogen gets used up. Okay, for every 1 mole of nitrogen, I need 3 lots of hydrogen. So if I'm using 5 lots of nitrogen here, I'm taking away 15 moles of hydrogen here. But 12 minus 15 gives me minus 3 moles of product of this left. Clearly that can't make sense. You can't have less than nothing of a substance. So that suggests to me that this scenario is wrong. And so the other scenario must be correct. And let's run it through just to show you. Okay, so let's say all of this is being used up, and then the nitrogen is limiting. Is excess, sorry. For every 3 moles of this, I need 1 mole of this. 12 moles of this, I need 4 moles of this. Which leaves me with 1 mole left over, which makes sense. So unlike the other one where I got to a nonsense answer, I have a logical answer here. So this one is correct. And what that then now means is that I look to this substance, the limiting substance, only to decide how much product I make. So for every 3 moles of this that react, I produce 2 moles of this. 12 moles of this that react, I'm going to produce 8 moles of ammonia product. So what I've been able to use, this concept of limiting and excess reactants, looking at the two scenarios, one reactant is limiting, and then the other reactant is limiting, to then be able to decide which one it's going to be, and then using that number only to then predict how much product that we make. Now, depending on the question you encounter, you have to be careful as to, okay, what's being asked of me? Am I being asked to work out how much product I make, how much reactant I use, or how much of the excess is left over? So that's where you don't just kind of plug and chug with this. You need to actually kind of work it through logically and then try to look at what the answer is asking you to find. Okay, so in this video, we've looked at this idea that in real-world chemical reactions that one reactant tends to run out first and limits how much product that we can make. That reactant we call the limiting reactant, and the other reactant, or reactants plural, that are left over at the end we call excess reactants. We have a process using stoichiometry we can use to calculate which is which, and then use that to make predictions in our chemical reaction. All right, thanks very much for watching. Bye for now.